to remove variation between sample and sample. Sample to sample, because to sample, yesterday I mentioned the urine case, yeah, very concentrated the urine and very diluted the urine. Actually, the urine itself, we want remove unexpected variation against internal standard, against or total intensity, against or some endogenous compound intensity. So there are among those one, total intensity is the most common method as the first step, but you can try with the internal standard. But sometimes this kind of, in this step, there are two words, normalization and scaling. I'll explain later, scaling in multivariate data analysis. Some people, they are confused. Scaling is, I will explain later, is peak-to-peak variation. Yeah, we have to use it. But normalization, sample-to-sample variation. Sometimes you weigh, you believe 30 milligrams, but it cannot be 30 milligrams, sometimes 20 milligrams, sometimes 35 milligrams. It's because of balance. Even you use very accurate precision with high precision balance, but we never know the water content, right? Sometimes it's completely dry, 30 milligrams, 30 milligrams, but sometimes it's yeah, wet sample that is not 30 milligrams. In that case, you have to use actually normalization. I explained a lot, but basic idea is sample to sample variation we want to remove. Everyone understand? Third, now is this an option or we have to mandatory one? I think it's a mandatory. For example, if you do raw sample, like this one, max peak. What's the max peak? As I mentioned, when you measure animals, the urine sample, the biggest signal, I'm not interested in that. All the signal divided by biggest signal. If it's a glucose, then divided by glucose. Also, it's possible, but it's not often used. And mean value, and median value. Something like this one. You can tell raw data is more or less the same, the outcome is completely different. Which one is better? There is no best method, but you have to choose one of them. Or this one is just a computer list. After it's like a post-analytical method, you can use any of them. So now in the row, max, peak, or median, all the data are completely different. Then commercial software, nowadays this processing you cannot do manually. You need a software. Which kind of software are you using for food processing? HMS? Is it MZLab or MetaLab or XCMS? Those kinds of open source you can use it. Also nowadays, thanks to R software, there are many the softwares is available. You can try. Also, if you buy nowadays new HMS machine, all the vendors they have their own processing software. Animal cases, which one is a glucose software we are using usually the Amix. Well, Amix now is changed the name, the new version Amix software, but nowadays commercial one is Master Renova or the Canomix. Those kind of commercial software they offer the normalization. So I wrote this kind of information, but it's a bit old, yeah, information. Nowadays, if you do Googling, yeah, SMS, then I think it's more or less MZ1 for SCMS is very common. And free software for chromatography mass processing, free software, which means chromatography, we have to use alignment, right? Best part in SCMS, you don't have to do alignment. alignment I showed you yesterday. This alignment, rather you need algorithm. This kind of software you can find it. Yeah, you can find it. And nowadays, more or less, everything it's like a total package. Yeah, SMS and then they can offer all process. It's not only normalization, not only uh, alignment. They can offer. Yeah. And on other chromatography thing, okay, now it's most popular metabolomic profiling method is NMR and MES. But is that all? No. Any kind of chromatography technique, any kind of chromatography technique, you can use it. Actually, basically, as long as you have a data, chromatography, mass data, IR data, UV data, whatever you can use it. Be careful, depending on analytical method, processing is different. But NMR cases, I will show you later. LCS cases, I already showed you alignment, normalization, removing noise, filtering, for those kind of things is needed. But TLC cases, let's say TLC, thin layer chromatography. You are using thin layer chromatography, right? Thin layer chromatography is actually the best method, the fingerprint. Nowadays, one of the company, the only one company is produce the total package of thin layer chromatography. How do you do normally the thin layer chromatography? Now it's plain, you spot it by yourself, right? It's for the synthesis, the monitoring, or sometimes it's about your fractions, how much is pure or not. But now I'm talking about for the chemical profiling. Then this kind of a manual spotting is not enough because every time it's changing. So that's why we need some instrument. And also solvent cases, TLC. Now it's TLC, the retention time we call it RF value. RF value is an accurate one, but there is a factor. Which factor it is? Humidity, water content, and also ratio of the solvent. Those one must be controlled. Like this one. Now your TLC is not like this one, right? No. But I did it. It's not my not example. So you can do this one, then which means all bands can be variable and intensity. Now, compared to LCMS and GCMS or NMR, let's check it out. Then what's the variable here? NMR cases, chemical shift and intensity. Mass cases, I told yesterday, I showed you intention time, molecular weight, molecular temperature. And TH cases, RF value. That's the variable name. Then intensity of signal. At THC, there is another variable, another outcome. What's the outcome? Because LCMS, GCMS, or element does not have a color, right? Only intensity, right? TLC is imaging. Yellow one, blue one, even in the same RF value, you have to do analysis. So that's why animal treatment, the TLC treatment, I want to see nice thing. This one, so that's why now this one, you have to treat it in all the time. TLC, data processing, we use image analysis. The image analysis is like a photo analysis we use. And nowadays, this one there is some open software you can use, which means now retention time. For example, retention time 0 to 1. 0.7, which color it is, RGB source here. So that's why 3 outcome. How much is the percentage of red color, green color, blue color? But the animal cases only depend the chemical shifts intensity. Fishness cases, retention time, and the amplitude, molecular weight cases. But this one is they show one value detention time but three outcomes. This is different. So that's why when you want to apply new method, always think about the character of your analytical. How can you decide the character? What's the variable name? Yeah? What's the outcome? NMR, once more, this is the chemical shift intensity, right? And SMS, detection time, energy, intensity. TLC, RF value, but R color, G color, B color. So that's done. Now, I needed image analysis. Even this TLC, from this TLC, it's okay. Do this case. But nowadays, you don't have to. When I started this one was around 15 years ago, I used, MATLAB. Yeah. Nowadays, no one is very few people using. Why? Because it's not free. Yeah. Instead, we are using R software. Right? R is a free cases. But when I use this one, I use the MATLAB M5 of image analysis. But I use it. But this one looks quite good. So in this case, TLC based on TLC pattern. We don't know, except for some few phenolic compounds, we don't know compound. It's very good and very cheap method. It's for the medicinal plant characterization cases. So that's why CAMAG, CAMAG, one of the company, that in Switzerland company, they have a very nice data source come up. You can do Google. It's okay, Google. The cases, please type in the search, look into the online, it's a gamma cache database. Then if you are interested, always one kind of mobile position, then you can find it. This is very nice. So don't look down TLC. TLC is a fingerprinting, is very nice. And I reported at least some years ago, our LCMS completely out of order. And NMR completely out of order 1.5 years because of magnetic problem. Then I didn't have anything to do. Yeah? So that's why I developed the TLC. Now, TLC is quite often to use. Please think many people have experience on TLC, right? Then, due to TLC, now think about so I have a question. What kind of another extra advantage do you might have? Best, okay. But when one was best, of course, SMS cases one by one. One thing is, TLC cases, you can draw parallel. Yeah, like this 80 sample, you can write up these cases. Maybe it's what? Still, compared to NMR, it's not that fast. Because you have to prepare mobile base, and then you start expanding time a lot. But it cannot compare to another one. Think about now you have experience with TLC. Now your estimate is broken. NMR is broken. Now you have to use TLC. There is no kind of advantage. Extract the pruning. No? Maria, you used a lot, right? Alisa, probably you will use it. This one. Preparative. Nowadays, even Mateus Alvarez, he said it's BIA or NMR identification cases. Always database is limited. Well, is not sure. Best way is like level 1. You have to isolate it. You have to compare it the compound, right? That's the best. That's the most accurate analysis. Then now you found it. For example, this one is very important bands, right? Important bands. I want to know these compounds. I want to know this compound. Then in the TLC, you can scrape out. Then measure HCl is much less. But of course, you can use HPLC. But HPLC of this one, you have to find which signal is HPLC is comparable as equivalent in HCl or in NMR. It takes some time. But TLC, you have to do this one. You take out, you measure. Nowadays, TLC, mass interface. Mass interface means you put the TLC, the robot comes, scrape out, wash, and so directly you can inject to the mass.
Say first about JIRS.
Yeah.
Because the young students needs only PBS, PBS, LC, PBS, LC.
No, that is still is uncomparable. But each method has a own tools. Now you have in kitchen, you have a very nice knife for cooking. But this one cannot be used for the peeling of your fruit, right? Each purpose you should use each, yeah, right? Each tool specifically. But in my opinion, fingerprint, and also I compare the same sample set, LCMS, NMR, and TSS. Most cases, for the separation that I didn't get, NMR is the best, always better than LCMS because there is a technical variation. But TLC also is not bad. Yeah.
Even if PLC made, when you apply the same tool, you don't reach it. But when you do this network, apply the same tool, you're just simple.
That is a manual problem. So that's why when you do automatic spotter, then you can like a rope, like a how say in HPC rope, right? It's a rail line bell. You can take out 25 microliter or 50 microliter, 100 microliter. They spot all the same. That is one. Okay, now it's preparative work. Another advantage. This is a preparative. This is a kind of a preparative. Another one. Think about this one. You know all of this. I want one.
We can use network agents by their
Very, it's this point. Now it's PLC. Now same plate, you can prepare same plate. I want to see, I want to see only alcohol, then drag and drop.
Yeah.
Or you want to see the phenolic, flavonol, then you can do with the natural product reagent.
Right.
You want to see double bonds, then iodine. Something like this one, very general detection with a very specific reagent. That's the maybe you can rediscover this, revisit. So this one now is what's this? Is a spanner. I have it. Nice, yeah. You put the test plate and then you control here and solvent. It's a wasp. Later, automatically spotting. And this one, what does it look like? It's like a developer. You know, it's not glass developer because you have to control humidity. Whatever this one is being used. It's not new anymore. It's very long time ago. Now it's available. And software. Now, alignment cases, TLC also must be aligned. But different manner. You cannot apply algorithm in HPC. Why? TLC cases is when you do plate, always do edge effect. TLC bands, here RF band looks like this one. Yeah? It's like always it's edge effect. Close the edge. Close the edge, the tension time is bigger. Yeah? So that's why to avoid this one, you have to keep some distance from the edge. Second one is alignment. It's kind of a similar algorithm. Do you know camera lens, fisheye lens? Then you can see like everyone looks like a fish, and it's like a macro lens. But they reduce this one, like this one. That kind of algorithm you can apply to the TLC align. You have to do it, but this one is included in software. So that's why alignment, normalization, or all kinds of processing, you have to understand very carefully all the analytical tools. Okay. Then now, TLC cases, as he mentioned, drug drugs or natural product reagent or Alice earlier, use it. When you do this reagent, then it's chemical exchange, right? And then actually the chemical reagent occurs, or chemical reagent, after reagent, it can be visible. That was the point, yeah? Because now here, in this case, it's a ginkgolide. Ginkgolide, I can treat it with acetic anhydride, but without acetic anhydride, you cannot see. Then this one is flavonoid. Actually, this one is treated with the natural product reagent. It's a name, specific reagent. Without this one, you can see UV. Then when you convert this one to the data method, that is there any problem to do chemical reaction? Because after chemical reaction, you don't know whether this one is yield 100% or not. I put it here, you convert it 100%. The same compound, 90%, 70%. The data is the clinical variation comes out. So that's why THC, yeah, intensity technical variation is because of the reagent. But in the expert, the THC, if you can do, please do not for the provided things. In emergent, what is a very unsuccessful case, like this case is you can do, but we have to consider this data. This data is visualized by chemical reaction, which might be chemical variation. HPLC, UV, and CEMS. UV also is possible, but UV, IR, LCMS, you said is a peak, right? NMR cases, how do you call it? Peak, signal, well, sometimes resonance, right? Sometimes resonance. The name is different. But UV or IR cases, UV, IR cases, I don't want to explain. Blood. UV cases, do you say UV peak or IR peak? No. Instead, UV band, IR band, because it's not peak. Then this kind of IR, UV band type of signal, of course, you can use it. You can use it like you can use it. For example, UV spectrum. You got it here. This one. Now, then is only two. If you treat it this one, if you treat it this one, it looks like a whole spectrum, only two signal. You understand? Then it's not multiplied data analysis. You lose the information. How can you treat it? IR also say IR looks like this one, right? Then only three signal. Yeah? How can you increase? Because multivariate data analysis, which means now metabolic flow, right? I want to get more information as many as possible. But now you need band type of the spectrum, you have only two or three, because it's a band. Think about
Maximum value.
what else did you say?
By my point of view, shall I add?
This one is, for example, 200. Now it's variable. When you, for example, you measure one, 400 nanometer is this here. 300 nanometer is this here. But this one is a continuous one. If this one is the best way is, yeah, here, for example, it's 200, 300, 400. Now, actually, this should be same, right? The best way is there any way to convert by peak time? This is important because then this variable are independent because that's very important. But this one is not independent. How can you make it deliver? You can use derivative. You know, mathematically derivative. Here, the derivative, 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 then it's converted like this case. So that's why when you are using data processing IR UV spectrum, UV is very nice for the wine analysis, or IR is good for the coffee. Then in that case, after taking out this one, no, alignment, because the band is not, you don't have to do alignment. Yeah, alignment you after derivatives. Then how many derivatives? Second derivatives. Usually official one is not first derivative, second derivative. Because derivative is mathematically is slope. Yeah? Each band is a slope. For example, now here is slope is zero, right? Zero. This one is here. This one is negative. So that's why positive, negative. But sometimes, many cases, the first derivative is not enough. Usually, IR, UV, when you look at the paper, two second derivative, not first derivative. But in my opinion, sometimes you have to check raw data, first derivative process one, second derivative process one. When I compare, sometimes, the most cases, second derivative is better resolution, better separation power. But sometimes raw file, also raw file without any derivative, also is good. And CE electrophoresis, because it's a capillary electrophoresis, it's like electrophoresis in molecular biology. What is the requirement of the compound? Compound should be ion. That one is used for catalysis or nucleic acid derivatives, cerebral spinal. Those one we can use. So non-chromatographic method. This one is a very limited. I cannot explain SMS, GCS, or LMR, but basic concept of this one. Now, I already explained to you in the nature, this one looks like an atom, right? Atom. Then here, nucleus located here. And here, what's that? This one? It's electrons. And this one, atom to atom, is a bond. So, higher infrared mode, longer than red reason this one is vibrant. Of course, they are always vibrating like this way, but if you give the higher range, is vibrant, is excited. But if you give a higher range, this one is excited, but not this one. But if you have a lower wavelength in the UV, like a UV, then these electrons excite. If you give a very low frequency, 1 meter up to 5 meter, then this nucleus, we call proton, is excited. So that's why sometimes we misunderstood, because if you have a shorter frequency, energy is higher. Driving a sort of frequency, everything is excited. No, it's not true. They have their own preference. And then now you have your situation. Your situation is amino acid, alkaline, carbohydrate in plants here. Because if you have an ideal method like a camera, now you hold the camera, then there are two kinds of choice. First one is macro lens, right? And you want to see the moon, then macro lens. You want to see the micro, need the micro lens, yeah, micro lens. But unfortunately, at this moment, you have to choose lens. If you want to go this direction, as the first profiling, I want to see amino acids, alkaloids, carbohydrates, flavonoids, all, yeah, roughly. We call it overall macroscopic metabolomics. They use letter to the B and one is. But now now you want to do detailed one. We have amino acid, alkaloids, and you will use SMS, like example. And I'm not interested in number of compounds. I want to do fingerprinting, whether this one is genuine or not. It is either band type of metabolic fingerprinting or TLC case. So NMR, very short example. Maria, you are expert. I heard it yesterday. You did a lot, great job of all the identification. Yeah. NMR cases, let's take the one. Simultaneously observation of wide range of chemical classes. This is the difference. Wide range of chemical is from mass, but chemical classes is from NMR. And easy quantitation without reference compound. Why? Now, since 2000, I also say about that one. Have you heard about the QNMR? Quantitative NMR. Quantitative NMR is nothing with the hardware. It's something with the concept difference. Now, if you want to check the purity test, purity by HPLC, what's the best way? You have to buy voucher samples, 100%, 99% you bought it. You compare with your compound based on peak intensity. Okay, my compound is 77%. That's what it says. Even this one is really the calibration. But NMR cases, you don't need it. Actually, the basic idea is all the intensity of the signal proportional to the number of proton and plus gold concentration. Gold concentration. So that's why in this case, NMR should select the internal standard. It's rather yeah, it's not less important than master. And non-destructive method. Non-destructive method, if you inject mass spectrum, you cannot recover. But animal cases, after plasma, you can recover. But actually, this one is not valid anymore. Even with LCMS nowadays, GCMS, you inject only 1 microliter, or less than 10 microliter. It's nothing. It's nothing. But still, it's after NMR. If you don't have it, you get it. Good. And high throughput. Why? Because NMR is takes only 1 to up to 10 minutes. One analysis takes 10 minutes. And independent on instrument. This is very important. Animal cases, if you do glucofile, glucose you are doing natural sample. If you want to combine this one, it's rather difficult because sensitivity, all the conditions are different. Even you measure today, 107, and 2 years later, he wants to continue this project, but technical variation is too high. We cannot combine. So that's why always at HMS cases, we need, this should be continuous measurement. Otherwise, we cannot combine. Of course, many groups, nowadays, they want to combine to remove that kind of technical variation, but still HMS, and GCMS, even GCMS also, there is some problem. But animal cases, even I have a group of 600 megahertz, and he has a developer, 600 megahertz. I said, he measured some sample. I measured some sample, we can provide, no problem. We call it a range study, no problem. And also, even he has a gel, different brand. I have a glucose, also it can be combined. Of course, there must be technical variation between the two instruments, but it's much less than other. Do you agree?
Yeah, completely.
So that's why LCMS cases, except for GCMS, sometimes when you are used the previous data written in the text, we have to be careful because they always write it basically and some important animal cases, whatever they wrote it, you have to see in your spectrum. And no need sophisticated data processing. Yesterday I introduced you full process of estimates, filtering, normalization, or nothing, blah, 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 but it's fun. And that's why every day new algorithm for the best data processing comes out to improve something. But animal cases, two reasons. Because it's less sensitive, the very robust method is only more or less only one method is available. And alignment, we call it binning or bucketing. The binning and bucketing, what do you mean? Now, here, this one is peak, and this one is peak. LCMS chromatography, but we are using algorithm, right? Working for this word. Animal cases, you don't have to do just integrate, calculate certain area here. This area, change it. Here, change it, no problem. That's why we divide it. How much is it? 0.01 ppm or 0.04 ppm? Always there is a debate question. The final is better, right? Because then more values comes out, then we can keep the resolution of raw data. But if you have very fine bucket size, sometimes peak is in the another bucket. So that's why we tested it 0.02 ppm in 600 megahertz or 0.04 ppm to be optimum of this. But in that case, if you have the rather bigger size of bucket size, probably in one bucket means two signal. That is also sometimes problem. So Beijing of animal here now is I told you ultraviolet is for electrons. And here iron is for pulse. Animal cases is a radio frequency here. Now near NIR is microwave. Do you know the mechanism of microwave? Because of microwave can excite, can make the hydrogen bond excite. So that's why if your food stuff contains water, hydrogen bond, they are excited, they absorb, become hot, right? Become hot. So that's why NIR case is also targeted is a hydrogen bond. And animal cases now is just let's demand. There are many names. Many names of analytical tools. But of those names, the best name is animal because of IR, infrared spectroscopy. What does it mean? Just the infrared spectrum. This one. But animal cases target and where and what's the mechanism? Complete if you understand the name animal. Yes. That's it. So nuclear, our target. I'm not animal is targeted only nuclear, not electrons, not protons. And magnet. We need the magnet because we cannot detect this frequency. This one should be in the magnet. Right? And then what's the mechanism? Resonance. 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 What is resonance? In the chemistry or physics, what's the meaning of resonance? Oscillation, like this one. Now, or any kind of movement in the nature, it has a waveform. Waveform. You like music, Kuruni? What kind of music do you like it? Korean music. Yeah, what about you? If I turn on, she has own frequency. On frequency K-pop, let's say she's K-pop frequency. But if I turn on different frequency of classical music, she never be excited. But when I turn on Korean music, she is excited because she observed this one is a resonance. Some decades ago, I watched a film. There is a bridge in the stage. It was okay. It was okay, but one day it collapsed in a second, in a minute. Why? Because always the California area had a very mild earthquake, earthquake this. And also bridge also always they have their own oscillation. One, it was okay for the time. One day it was resonance. Then it's moving this one. That's what resonance is nothing with the energy, it's a matching. This is okay. Then all nucleus carry a charge. This is the nuclear charge. What's that? Because this one is a basic. Many people know already, but I want to remind you. Nucleus has a charge. Which charge it is? Plus. The plus charge. And then in some nucleus, this charge is on the nuclear axis. Not all the nucleus, some charge. So that's why we call it magnetically active. Magnetically active nucleus. The best one is proton. Proton, hydrogen. Because we never say hydrogen NMR. Of course, we write H NMR, but we never pronounce it hydrogen NMR. Because our target is not hydrogen, our target is nucleus of hydrogen, so we call it proton NMR. But in old times, they used in the textbook PNMR, which means it was proton NMR. But nowadays, we never use in the writing form PNMR. Why? Because it's confused with the phosphorus. Because phosphorus NMR, ADP, whatever is for the, this one is very important, one is confused. But anyway, project, the proton NMR, nucleus spins. So nucleus plus charge. The plus charge is spins moving. Yeah. Spins moving. Then in the nature, if nucleus charged material is moving, what is generated? Magnetism. That is, I'm not, maybe it's easy example. Brazil, I don't know, on the top of the mountain, there is a high voltage. Yeah, high voltage there. There is a warning. Yeah, don't get close, then you will die, right? Because ions, charged material is moving, then magnetism generated. Now you have a bubble, you touch it, then you will be in the happy life, in the heaven, not here, right? That's it. So that's why charging the material, if it's moving, then magnetism generated. What's the magnetism? North and south, right?
Yeah.
Let's keep in mind. And then that's why the angular momentum of the speeding charge can be described in terms of a quantum speed number. What's the meaning of quantum? Because it's one of the revolutionary concept in the 20th, 19th century, the end of 19th century physics. Quantum means, because you heard you learn quantum, right? What's the meaning of quantum? What's the meaning of quantum?
Means safety level. You can change it from one level for other level, but one specific quantity.
Yeah.
It's quantum. One quantum, two quantum.
That is a very good important one. If I translate each word in Newton physics, we believe any kind of value in the nature will be continuous. Yeah, one. After that, 1.0001, 1.002, it's a continuous variable. But 19th century, Max Planck, he found it. No, nature is not like that. Always discrete level. After one, there is no in between. 2, 3, 4. They found it is spin character. On the spin character here now is 0 and half. 1, 1.5. Now, there is no in between, so that's why there's the quantum number. Then this one is just a character, like a density of the molecule, the substance. This character, then 0, 1, 1.5, 1.5, 1.5, something like this one. Each atom, so each proton, each nucleus has its own spin number. Spin number, how can I distinguish? Then NMR, detectable atom is non-zero one. 1, half, 1, 1.5, it can be detected. Any kind of protons, you can detect. But problem is, we don't know, because it was made by God. How can I know? There is some finding. If you know this one, atom in the periodic table, upper one and lower one here, right? Upper one, lower one. One of them is atomic mass. Atomic mass is number of electron or proton plus neutron. And then the other atomic number is electron number or proton number, right? H1 here, this C13, 6, something like this one. And now N15, 7, like this one. If one of the number is odd number, then magnetically active. Now H here 1 and 0, then is magnetically active. Carbon 13, 6, 1 is the active. But our most abundant isotope of carbon, 12, 6. Unfortunately, you cannot get oxygen, 16, 8. No, instead, always we are using oxygen 17 is isotope level. Tell us the level. So that's why organic chemistry always their dream is I want to detect the carbon because carbon is the backbone. Why we have to use proton? Because carbon 12 cannot be detectable. Instead, carbon 13, 1.1% natural abundance, you can detect it. So that's why when you do animal cases, carbon 13, when you measure it, it takes 1 day or in same concentration or sometimes 1 week. So that's why we cannot use it. Although it's very much information. So now, this one is a very basic example. It's I told you, some material, proton, is spin, right? It's a spin. Then, if this one is a spin, magnetism generating, right? North and south. So then now I explain why I have to use magnet here. Now, all the protons or all the nucleus, they are behave like this way. Different directions. It's like you now you aligned very well, but just before the class, outside the classroom, randomly, even though you have a magnetism, some people are drinking coffee, some people are chatting, some people in the toilet, but now you align like these pieces. But everything is now aligned. So that's why we need this magnet. Then why we need to align this one? Usually, here. North is our magnet, animal magnet, and this one is the south. Then everything is like these cases, right? But in nature, it's not like that. Now everyone like this. Half of them, they are very much interested in this course. Half of them, they are not. Who cares? Today is weekend party. I'm interested. Always it's like this one. If you put this one is half, almost half. Now it's a bit more. Half is well aligned. Half is anti-aligned. Right? Now this one is well aligned. You are very good students. This one is very bad students. And this is right. Actually different. Very slightly difference is right. Yeah. So this guy, in the good part, only one is, the other one is only different. Now, I prepare frequency. I prepare the frequency. When I give a frequency here, you are very strong will. I want to learn. They have a very strong will. I don't want to learn. But this guy, when I give a frequency, change the number. Life is life. He will is likely to be here. Yeah, because I gave an energy. So that's why, in this case, NMR, we have to give a radio frequency. If you don't give it, she's not activated. Maybe I can give a frequency. He moved. Yeah? He enjoyed the life. But of course, basically, he was a very good student. He was a very good student, right? But then after that, he regret. Right? Because he was a basically good student, he returned. And he released the frequency. I intend. That's the mechanism. Very simple. Right? I didn't use any mathematical model, but only this case. The light is always natural light, human light, the same. Then, what is the animal intensity? That's the of this one here. Now, frequency is in between this distance. Because if he wants to move this distance, he needs some frequency level. If it's a bigger, the discrete level bigger, then the intensity is bigger. is bigger. So that's why then this distance factor is magnet strength. So if you have a very strong magnet, the distance is bigger. Like this cases. Like this cases. If it's bigger, then they move and they move. This is another factor is here. So depending on the character of nucleus. So proton is usually like this. But due to the inherent character of carbon 13 like this one third, we call it magnet to Gini ratio. You're gonna remember. So that's why when you compare proton and carbon 13, the first factor is compared if proton signal is 100, carbon 13 1.1%, right? Another factor is the intensity is one third. So that's why real intensity of carbon 13 NMR is 1.1 multiple 0.25, 25%. So that's why very low. Then information, that is the basic one. Why I give this course? Because always when you want to learn NMR, first three chapters always is very difficult. Always is very difficult. If you want to learn NMR, just skip first three chapters, starting from the fourth chapter, how to apply. This is more than enough. Because this basic concept is more than enough to learn by yourself. And then information from NMR cases. Now, 1D NMR, actually it's a 2D, but we call it is 1D NMR, chemical shift of this, the chemical shift of this, and then signal, this comes out, But 2D NMR is chemical shift. There are many combinations here. This looks like this one. 2D NMR looks like behave like SNES, right? Retention time, empathy. Then you might have a question, why we are not using 2D NMR for the multivariate data analysis? Because proton NMR is not enough, yeah? Sometimes 2D NMR is possible, but many of 2D NMR, this intensity is not quantitative, except for few cases. So that's why still we are using this proton NMR. Then, now, this one, the proton NMR. Now, proton is a frequency, this proton's frequency, this proton's frequency, this proton's frequency. Then you might have one question. If proton is the same, they should absorb the same frequency, right? Why they are different? But you are proton, then you should have the same, you should absorb the same frequency, right? But NMR cases, when you measure the NMR, each proton has its own frequency within range. What's the question? This is okay. Although I targeted the proton, but this proton is influenced by electron. This electron is here. Electron is minus charge, plus charge, right? Now, because electron is like your unloyal girlfriend or boyfriend, always is interested or she's interested in others like this one. Then now his plus is very free. He's rotating fast. So that's why his frequency, this situation is different. So that's why some people misunderstood. Okay, target is the proton NMR, but our target is the proton. As he mentioned, it's because of environment, that environment, the electron is always is movable. So now,
Can just one point.
yeah,
The scientists who have the first idea about the 2D and just died on the beginning of this month. Engineer, he is the guy who posed the first idea in Ampere in 1971, 72, and he died on the beginning of this year. There are some honor for this guy because the real idea was from engineer and
he died. Actually, the 1970s who developed the whole study, the concept of the Ernst, I guess you should know.
Yeah,
He got a
Ernst,
Nobel-
Ernst.
Ernst, he got a Nobel Prize winner. Nobel Prize winner. But some people misunderstood. Who can be the laureate of Nobel Prize winner? Of course, you know the Marie Curie, but actually it's not the lecturer, but Marie Curie or Albert Einstein, right? But actually Albert Einstein was not laureate because of his theory. It's because of other. Usually, I, my feeling is Nobel Prize laureate is based on how to apply. Nowadays, so that's why some 2 years ago or this year, the guy who developed the lady developed the imaging technique guy. And 2002, as I mentioned, the Shimachu guy and the American guy, because he developed magneto and mass technique. That's why, rather, if you want to do Nobel Prize winner, technique is also important. In the beginning of this course, I said, you are scientists, you should focus on the above level, but technique, it does not mean I look down the technique. Technique is also important because it's a potential to solve other questions.
Education is not important.
Okay? Clear? And spin coupling, because NMR is not one signal, always NMR signal is several splitting. Because if I have a frequency here, you have a frequency, yeah, frequency, and there is a frequency. Yesterday you sang blood, right? You sang blood, but when you are singing, we need accompany music, right?
Yeah.
Accompany music like a guitar, guitar or piano, whatever. But after this one, together with this one, there's new sounds coming up. So that's why be careful in animal signal, like mass. Always you have own frequency. If this frequency is very similar, close to other frequency, they are splitting. This is clear. But of course, the detailed one, how much is a triplet, doublet, you will learn from the book. Anyway, animal signal, one signal is can be split. That's another thing. And also basic character of animal spectrum compared to mass spectrum. Mass spectrum is for example, each patient part, one peak, one compound. Right?
Yes.
One peak, usually one peak, one compound. But when you do LCMS, one peak, several mass comes out, right? But animal cases, one peak is not but one compound. Instead, you can think about animal is kind of a mixture of fragmented eye. So that's why when you take out one animal signal, it does not mean original is a compound, but it means it's a fragment, some part of structure. Then part of structure, how can you get the assume the structure? Because the characteristic signals are there. Maria, you have a nice structures. You showed the nice structure. When you measure your plant material, plant material, now you know which signal is very characteristic for your compound, right? Right. This is so that's why alanine case is 1.5 because there are other signals, but animal identification basically all the fragments is coming out. Among those one, this one is very characteristic. Since 1999, then we decide, okay, this one is 1.5 doublet is alanine. 1.3 is lactic acid and threonine. 5.2 glucose, alpha glucose. 4.6 beta glucose. I can remember everything. Well, this is a kind of characteristic. A little bit, it's a primitive identification, but still we can use it. So basic split coupling, and in animal spectrum, three kinds of information we can get. Chemical shift. Chemical shift means chemical. Why we like a peak mass case is always I compare mass. Mass is retention time. How much eluted, right? And mass part is what is the molecular weight, 300, 400. But animal cases, they are using very strange word, chemical shift, right? 1 ppm, 2 ppm. Why? Maria, why we are using the name the unit of NMR is chemical shift. Chemical shift.
English.
My English, probably it's my English, because it's my English. Sorry, so, but that is why chemical shift frequency is your frequency. Now you are in good mood for learning, right? But if you yesterday you are in the drinking, right? Your mood is changing. Animal is everyone has a frequency, but it's changed by environment. When you are in the beach, it's a beach type of frequency. When you are in the same one is when you are doing in the sorry the in the classroom, it's a learning frequency, something like this one. Yeah? But then now if I put it in the 400 megahertz NMR, its frequency is, for example, 1 hertz. But same compounds I put 800 megahertz, it observe not 1 hertz, 2 hertz. Now, if you are using this absolute value of its frequency, I have to write which model I use, which model I. This is very difficult, right? And also, now one of the advantages of NMR, we can compare 400 megahertz NMR, 800 megahertz, no problem. To avoid this one, yeah, in NMR, as I mentioned yesterday, one of the role of interstandard NMR calibration, I put one calibration here, yeah, here, when I put together to this one, always the ratio from here is different. So that's why he always observes 0 hertz, for example, yeah, some hertz. And this distance, even though absolute value of this one is every time is changing, but its ratio is not changing. So that's why from internal standard, how much is shifted. So that's why it's shifted. But the level is ppm, part per million. So that's why 1 ppm, 2 ppm, 3 ppm, 4 ppm, or something like that. So that's why NMR is like so strange, yeah, strange unit. They are using chemical shift. And now NMR is now is another issue, is a technical issue. Is NMR case is I told you is a deuterium solvent. We have used deuterium solvent. Why? Because if you use normal solvent, methanol, only methanol is detected. Methanol is detected. So that's why we have to use deuterium solvent. Yeah. Instead of H2O, you have to use D2O. D2O. But two questions. If you do D2O, you should not see in the animal spectrum solvent signal, right? But always when you look at the signal, the biggest signal usually is a solvent signal. How is it possible? Because even I voted 100% deuterated solvent, I hear it, there should not be, yeah, there should not be solvent signal, right? But there is a big solvent signal comes out. Why? Simply
and the concentration of the reaction twice.
Simply speaking, there's no perfect method to make 100% deuterium solvent. The 99.001%. But even the solvent ratio 99.00001% purity, but still compared to compound, it's high. So that's why solvent is not very high. So that's why when you do processing the animal spectrum, the solvent signal should be delayed. Depending on the solvent, the chemical shift here. You can use this one. And second one, it's not only this one. Which one you have to delete it? Water signal. Water signal deleted. Why water? Because even though you are using water-free solvent, but your sample has a water signal. But now also you open the solvent, all the water from the air, even is coming to your solvent. So that's why practical tip is when you take out deuterium solvent from the fridge, please do not open. Keep it warm and then open. Then you can reduce the solvent. So that's why water signal, water is H2O, yeah, because animal is detected its water signal is so high, you have to remove it, yeah, you have to remove it. So that's why first freeze dry. Second, water suppression, water suppression, and third, delete. The problem is water signal, chemical shift. Here, you get this one. Here. Now, when you measure chlorophyll, water in chlorophyll, of course, what chlorophyll water is not missing, but small amount of water, 1.5 ppm. And then ethylene chloride, 1.5, and pyridine, 5 ppm. It's a very, very different this one because of hydrogen bonding. So that's why when you take out processed animal spectra, you have to be careful. Where is the solvent signal? Where is water signal? Also, when you choose the solvent, you have to think about this one. Then in animal spectrum, OH signal, hydrogen bonding signal, is we call it is chemical shift. It follows Murphy's law. Murphy's law is we cannot expect. For example, phenolic compound is 7 ppm exactly. Olefinic compound 5.2 ppm. We know already. But any situation, what? But hydrogen bonding signal, OH signal, this one is varied. Yeah? For example, now it's the same compound, but if you measure concentration, now is your molecular OH be close together. So that's why this OH signal is really changing. Also, another one is temperature. If you change the temperature, increase the temperature, there's no connection, chemical shift is changing. So that's why temperature, you have to fix it. Then concentration, you have to fix it. But even this one still is valid. So that's why in the animal metabolomics, we are not using often chlorophyll or DMS. Because chlorophyll, DMS, or chlorophyll, DMS means if we have a compound with here, chlorophyll does not have any OH proton, right? DMS and OH proton. My OH is still alive. So that's why it's detected. But if your compound, my compound, is dissolved in water, this OH replaced with the deuterium. And this one is not detected. So that's why when you do structural elucidation, first OH signal is very important. Yeah, sometimes you need it. But when you do metabolomic, OH sometimes 1 ppm, OH sometimes 2 ppm, OH sometimes 3 ppm. It's very annoying. But in that case, always we are using protonic solvent. Proton or methanol base, not DMSO, not propro. You understand? Methanol or is a mixture. As I propose, 1-to-1 mixture. 1-to-1. Do you understand? Shall we have a few minutes break?
Yes.
I think they look higher. Can you have some 15 minutes break? It's okay? Okay. Because I'm drinking coffee, but you missed another coffee. I finally today I found your passion from your eyes. It's the first time for me, so that's it. 10 minutes break, 15 minutes break. If you don't mind.
Yeah.
Because it's an animal, it's more it's basic. Basic finish it. This animal, some people say, oh, it's too basic. Actually, this kind of concept, as you know, if you want to start some new thing, always it's very important. What I mean, my lecture is not enough for your animal learning, but at least I would like to make you start to learn animal ethics. And also, if you do, one day you will communicate with the animal life identification. You know already, then you can communicate, easy communication. It's like I'm learning Portuguese here, something like that, for easy communication. Yeah. Please, yeah.
Stabilize anymore. Comparing many spectrums, but you don't have to suppress water side.
question. So that's why there is animal step. Here, animal step, so now is depending on the solvent, water signal is different. For example, 1.5 ppm in chloroform. 1.5 ppm in animal is very important for all the terpenoidal signal. Yeah, terpenoidal signal. If you do water, 4.5 ppm, I know it. This one is usually for the sugar part, but it's a less crowded region. So that's why the solvent, one of the factor to select the solvent is where is the, if you want to do water suppression, I want to do the water signal in the non-crowded region. So that's why in that context, methanol water would be the best. And long time support, is one of the example is your tritterpene. You know tritterpene? Tritterpene, as I mentioned, characteristic signal is methyl signal, around 0.9 ppm till 1.6 ppm. So it's very well soluble in chloroform. I measured it. But the problem is water signal in chloroform is overlapped with the methyl signal lost. In that case, of course, nowadays we are not using, you should not use benzene. If you change the benzene, then water signal is coming at 0.4 ppm. So that's why sometimes it's not because of solubility, because of water signal, solvent signal you use. And also now you work saponin. Saponin, who is saponin? Correct? So since you're doing saponin, yeah? And you do saponin cases, saponin is usually there is no double bond. Maximum there is no phenol. The maximum is 5.2 ppm, right? And it's not soluble in water. It's not soluble in water. But if you do methanol signal comes out 3.3 ppm. It's completely overlap with your saponin signal. In that case, we use pyridine because pyridine is very polar solvent, same as methanol, but it's detected around 7.5. The signal is really non-crowded region, something like this one. So now still I read your question. Oh, yeah? Now, IR, yeah. So NMR, SMS, QCMS, and KLC, we touch. Actually, I need there's not any explanation, but at least I gave you talk about the characterization, yeah, characterization of each data set. Means you have to you don't have to understand all the theory or mechanism, but at least you know what does it look like. Then then you can make a list what I should like animal cases, solvent signal, water signal, and hydrogen bonding. SMS cases, whether it's detention time, shifting, and molecular weight cases, featuring those things you have to, and TLC cases, edge effect, and then data. RF value produce three kinds of data set. This is very cool. Then is IR. Also, IR is also is being used a lot, but for fingerprint cases, because IR is also band type of spectroscopy. Band type means raw data looks like this one, looks like this one, but you have to do second derivative. Second derivative. After second derivative, probably you need some like not in this raw data level. Raw data level. And also alignment. Sometimes it's a waveform alignment is possible, but it's nothing big. It's very different from peak type of signal. You have to choose optimal alignment software. And other is chemical fingerprint. This is chemical fingerprint. Very rapid. Very rapid. And another advantage is IR. You don't have to make a solution. Sometimes you already KVR network, the palette, you can use it. So that's why coffee bean. Coffee bean, if you want to compare the Brazilian coffee to Colombian coffee, then if you do animal or SMS, you have to extract water, water or ethanol, you extract, and then you compare. Of course, it can be possible work. Sometimes it can be good for the identification cases. But now you are interested in not only the metabolites, but it's the fingerprint, whether it's Colombian coffee. First question is different or not. If it's different, it's sustainable or not, then you can use it higher. Also, as I mentioned, the big pharma, every day, for example, they produce capsule or tablet at 1,000 or 10,000. You cannot do SMS, GCS, analysis. Then just a few seconds of higher spectrum is good. Yeah, and best example or well-known example discrimination between coffee Arabica and coffee Canora. I don't know which coffee it is, but Robusta also Arabica is also discriminate very well. And investigation plan based by metabolic fingerprint. Whether they are safe or not, this is just matter. Either, as I mentioned, what's the target? Between molecules vibration. Molecular vibration. But vibration, which means atom and atom, I have an atom and atom here. Here vibration, you should have only one frequency, right? That is not true because oxygen, hydrogen, hydrogen, one functional group, sometimes this, sometimes this, sometimes this, sometimes this. So that's why one functional group produce several bands. That's easy. So that's why these bands fortunately very robust. So that's why in all the time, even now, if you want to do whether chemically it's safe or not, iron is the best method. That is we call it stretching ending. So that's why one functional group, ideally in the textbook, they said IR is IR is a chemical fingerprinting method. Your IR is a range. IR is actually this one is we call it frequency, but it's not hertz because this one is only for the IR one and IR cases. 4,000 till 615 Kaiser. Kaiser, in this case, OH, CH, NH, or alkyne group, and very few bands, and ketone group. Those bands is possible. for the structural elucidation all the time. Protodenoma, saponin, or flavonoid, we use IR. Then what kind of information I have to rotate 1990? I found it orange. I found it ketone. I found the presence of double bond. But actually, those kind of information is already done by NMR, no problem. So that's why IR is for the structural illustration in these days is not mandatory for, but all times you have to. Now, then is I can give a tip for the structural illustration or for the chemical fingerprinting, which bands is the most important one is this range here, which signal. It's a really big band. So that's why also in IR spectrum, when you see the spectrum, always they commented. Yeah, they commented. It's a small, medium, large, something like that. So big bands, then medium bands, and small bands. In this case, OH big bands around 3,500. And this one is very important. And this one is very important. Is double ketone group 1,600 plus minus 100, depending on the situation. So this one is conjugated was a little bit shifted. These two information we use. For the structural station, for the chemical identification. But still one of the to use IR for structural station. What is that? The IR still is being used for one functional group. I told you IR is not really mandatory. It's not mandatory because most of the information can be obtained by NMR or mass or whatever. But one functional group still is important. What is that? This range. Not this range. Only one is triple bonds. Triple bonds, yeah. When you look at the animal spectrum, can you recognize triple bonds? Because in animal spectrum, triple bonds usually C, triple bonds C, which means if this one is inside the structure, there is no problem. If there is even is a terminal polyacetylene, we call it acetylene group, H is around 2.2 ppm. That is similar as there is no characteristic peak mass. Triple bond? No. Because we don't know which one is, whether this compound has triple bonds or not, mass, and what is the problem? But the measure, is around 2,000 to 500, 2,500, although it's a very small band, but it's non-crowded region. So now you want to know triple bonds presence in your spectrum, IR bands is quite nice. And then which plants contains a high amount of triple bonds containing metabolites, we call it acetylene compounds. Which one? Chrysanthemum. Chrysanthemum, we call polyacetylene cases. Long time ago, those kind of compounds was targeted for anti-cancer compounds, but not anymore. In volatile of chrysanthemum, AstraZeneca material, they contain high amount of triple bonds. But this is a very nice. But triple bonds is even double bonds is a fitness effect. Triple bonds, when you extract the triple bond, what's the problem? It's oxidized. So that's why you have to be very careful when you know acetylene is in your cell. Most of acetylene groups are in the volatile compounds, very small amount. This volatile, when you evaporate, any compounds are oxidized. And iron, coffee bean using iron, looks like this one. Here, look here. Now this is better, but this one shows the other way around. Yeah? Usually iron looks like this one. And here, this one is OH phase. And this one is double bond spans. And here, there is no ketone. Here, then it's a lot. And as I told you, this band should be second element. After that, we have a lab. Now, higher spectrum, 20 times, you can do the solid state measurement, no problem. What we should be careful. Now it's you learn it. Higher spectrum looks like this one, and what kind of band is very important? Higher bands. What's that? Wait.
Oh, wait.
Yeah, this is a good point. It's OH band because OH band is huge. Yeah, huge. It can be your compound, but it can be also from water, residual water. So that's why sample depending on the how to say the humidity or water content, the band's quality is completely different. You have to be very careful. Your sample, you cannot remove 100% water, but in either spectrum, water bands is yeah, it's coming here. If you want to quantify OH bands here, be careful about your dryness. And your coffee bean using IR band is the now is first one, second one, third one is voting something like this one, then they do Arabica, Arabica, coffee Arabica, and Robusta is here. Which one is good quality? Arabica is good quality usually. The Arabica is good quality, and this is here. And I have one also honey. Honey is really big, right? Because but honey, when you look at when you want to do metabolomics, honey, honey. So simple preparation. What's your Chris? What's your strategy? Now you have a honey. How to prepare the sample? Andre? No?
No.
Alicia, now you have a honey sample. Honey. Huh? Honey bee. You have a honey, very sticky sample. Now you collected all the honey, Brazilian honey, Argentinian honey, Korean honey. Now you want to compare. Yeah, first, yeah, compare. Then how to prepare the sample? Crystallography, but it's a liquid case. Of course, X-ray crystallography is inside, but X-ray crystallography is not very available. That is a common experiment. And
I guess it was water. Water moves.
Huh?
Water moves lights, first of all.
Yeah.
Each one I've seen.
You have to you have to do two things because honey case is usually sweet in its is from sucrose or maltose or sugars. Then you can take out first. I want to take out very mixed with the water, yeah, and then dry it up. I want to do GC-MS analysis because GC-MS is a limitation for the sugar, secret sugar.
Yeah.
I want to do GC-MS analysis, but important one is toxicity of honey, quality of honey. It's not because of sugar, it's because of flour metabolites.
Yeah.
Flour metabolite. Then I want to mix it with the fertilizer. What some SP method because the same as a honey, your sample is too much honey. I want to remove sugar and secondary metal, which might be from orange blossom or acacia. Now there was some years ago there was big scandal in Turkey. Okay, there is in honey because honey we can the bee we cannot control. They go to the toxic plant like a silicio, pyrolytic alkaloid they brought, and then in this honey there are a lot of pyrolytic alkaloids there. In that case, you have to use SP, solid phase extraction to remove honey or liquid extraction. But higher spectrum, whether it's a real honey or the maybe directly honey, you can measure higher. You understand? So there are several fingerprint. Now, do you want to see the fingerprint? Oh, fingerprint? Okay, then IR. So other method is fine. And second, do you want to see main metabolite? Okay, then it should be sugar. I want to do with nutrition. Do you want to see any minor amount of secondary metabolite after some several treatment? I want to do with estrogen, flavonoid, or something, or toxin related. Yeah. Then another one This one is direct diffusion. So direct diffusion means as like like cerebral spinal fluid, or you have a defined, very purified each cell. Why we have to use LC or GC? Instead, directly you inject the mass spectrum, and you can get all the spectrum mass molecule. This one can be used. Advantage is, what's the advantage? Disadvantage is we don't know which thing is which compound, but you already know based on molecular weight, and also it should be soft ionization. Advantage is short time, very short time, and also second one is you don't have to do a lot data processing, much simpler because it's only molecular weight. Problem? Can be overlap, but this is evolution is possible. Suppression, ion suppression. So that's why ion suppression means if you added too many signal with one major suppressed out of signal, only one signal can be detected. So that's why the first requirement for this direct infusion, it should be required. Most of the signal you expected in the same level. It's the same level and less. That's the direct infusion. So that's why some fluid like a flowing set or CSF, those kind of things. Okay. So technique, target, you have to match by yourself. So flow injection metabolomics you can do here. Sometimes is yeah. You can do also is based on mass metabolomics. Any questions?
Sure. Could you just talk a little bit more of this direct infusion? I didn't really get the last part of your talking. Yeah, it's like the main problem you just mentioned.
Main
Not
problem.
just fraction, but you extend a little bit more.
Yours, if you first one is if you want to if you don't want to inject through color chromatography, which means your data contains all the compounds in one mass spectrum. But when you do LC mass, peak by peak, you have a mass spectrum, right? Those less. So then it's more or less you know which one is a base peak, which one probably fragmented peak. But now one, all this mass spectrum in one mass spectrum, then we don't know which one it is, which one. Yeah. That's the question. Second one is, for in this case, is you should use not EI spectrum, instead you should of the ESI spectrum. Even then, fragmented ion comes out. And second one is, if metabolites are too many, that's complex. The second one is, if metabolites concentration is too different. One of them is 1 milligram per ml. The other one is 1 picogram per ml. Yeah. You cannot, if you do HPLC, 1 picogram can be detected because it's already separated from column to column. But in your direct infusion, you cannot detect the one small molecule. So that's why first you have to check it whether they are dynamically or less similar. So now metabolomics long time ago when they apply when they want to do protein, yeah, protein analysis, protein they are not through the HPLC and the separation of protein they use different infusion. You mean if we have several compounds, each compound must have an ionization ratio is different, right? Yeah. Then how can you get compounds. Yeah. So that's why I told you, like, first one is in the sample, better to have a very similar compounds, like the play acid. Then ionization power is more or less similar. If you have some flavonoid in the case, phenolic compound probably is similar, but your compound is one of them is sugar, one of them is flavonoid, one group is kind of supporting cases. Then your direct infusion is not of good. And also most important is the technician, mass spectrum, they don't like it because it's directly going there, it's contaminated.
So like for metabolomics is quite limited, right?
Yeah, it's limited, but I want to show it's possible because always there is a possibility.
I
And
had
I don't think we can apply. Your research can apply.
I got a data set from direct infusion of some plants in Brazil. They're like called banks. It's like in heat, but they are not popular. And I was asked to try performance analysis in this data set. So based on our talking, it's quite hard, yeah, because they are content extracts. So they do have all.
I think it's a data if it's a blood extract and then you inject the through direct infusion. Probably the quality of data is not as much as this is first. You know? But if you don't have any other option, you have a lot of infusion data, then you have to do statistical analysis. Statistical analysis, which molecular weight is very important for the distinguish. And that one is you have to obtain this one by HP, HMS, and then where which field is containing this one, then you can do one line. That is now you 1,000 spectra, you already did it by your friends, yeah? In direct infusion. So threw it away, and then I want to remeasure 1,000. No, already data, take it, and then treat it. This best data as well, animal data or HMH data. Then you can find it, you can select which ions, which ions. It's very important, right? There is a 300 or 600, and those are very important to see. Then you have a question whether this one is a fragmented ion or not. Then you can measure one of the sample based on what it you need SMS, which pitch contains this signal, okay, this one. Now 600, 300, 300 is the fragmented ion of 600. Probably this one is one compound, then you can start the identification by your. This is a general thing. Always, some people, you should not be stubborn to your protocol. Always can be changed. But once you start it, you have to be stubborn. That's my point. Always is whether, go or not, or go or not, before deciding protocol. Once you decide it, you have to keep it protocol.
CMC machine, unless combination, factor rotation with other that base machine PLC.
TLC,
Correlation factor with other base.
you mean the TLC with the mass spectrum, can it be used for the metabolomics data, you mean, right? Yeah, this is also possible. Yeah. This is also possible, but when you run TLC, then each bed you have to take out the mass, and now you use THC RF value instead of a THC band's color. You use SMS. Then it's a pity. Why you have to throw it away this part? First, my case is first I want to do THC RF value as a variable. And then outcome is the intensity of each color, and I run some statistical or multivariate data analysis, which means is very important for your research question. And I took out this one to go to the LCS to identify the compounds. That's the logic. So today is afternoon session, and tomorrow morning I will continue with the statistic and multivariate data. A statistic is it's a yeah, lifetime job, but I cannot finish it within 1 year. But there's some tips how to learn, because every day new technique comes out with algorithm, but basic one is very important. And now I want to overview about analytical method, just some points which I didn't mention. FT, Fourier transformation. What's the Fourier transformation? Chris, what's the Fourier transformation? Fourier transformation is a very simple. It's not only for animals. Sometimes FT animal, FT IR, FT mass. Basic is if the movement is following oscillation, like a sine and cosine, if the mixture of all the oscillation one, each we found it each frequency. That was the Fourier transform. So that's why animal, all the proton, yeah, they are excited. They have own, yeah, they have own FID, yeah, free induction decay. And FT mass, ion in the magnet, they have own frequency. If the ion also is available, they excited at the same time, then everything is then it's interpreted by Fourier transformation. Actually, this Fourier transformation in all the type of the machine, we don't use it. Like an animal case, is whatever all frequency, we call it continuous wave. Continuous wave means you like 1 hertz. You like 1 hertz, then I prepare all the frequency. I gave 1 hertz, you accept it. I gave 2 hertz, you accept it. So I do continuous wave. Then I know this one is 1 hertz, this one is 2 ppm, 3 ppm, 30 ppm. But animal is too nonsense, too insensitive. It's not sensitive. So that's why not? I can make them excited. but each frequency is very different. Yeah, very different. How can I make that at the same time simultaneously excited? I can give a center. Now you like it 1 hertz, right? You like 100 hertz. Which one is it? Center 50 hertz. I give his 50 hertz with a pulse. Then 50 hertz one time, and slowly second time, and slowly third time. Then his wavelength can cover here. So depending on this pulse, if we give a very fast pulse 50 hertz, I can cover very broad. But if you give a very slow, I can narrow range, depending on this center. I decide the center covering. But the problem is, new problem comes up. Why? Because when I'm using continuous wave one, I don't have to do any mathematical transformation. Only I ask answer. I ask answer. But empty cases. Everything is excited, very complex. You need to Fourier transformation. It's a kind of a revolutionary fair in the spectroscopy because we can reduce a lot of time. When you do continuous wavelength, the continuous wave animal, one proton animal, it takes 1 day. Because so we have to repeat several scan, number of scan. But continuous wave, we can reduce a lot of time. But it's not only an animal, it's a mass and ISO. And statistic is something like this one. There is a file. Now all the signal, SMS, 100,000 signal, animal signal. Of course, if you want to identify them, so now it's a different chemical profiling or metabolomic issues. Now you have your orange signal, Brazilian orange, Florida orange. Of course, hundreds of signals here, 100 signals here. Now we want too ambitious. I want to collect all the signal. Now I don't know which one. Then which signal is important? Now my case is what's the biomarker signal to separate or to distinguish Floridan and this one. Right? There is a value, that is something. You have to find it. Then if you want to identify the restaurant, it takes 8. But I want to focus this on by statistics. Statistics or multivariate data analysis to narrow down to select which signal is important. So general procedure method I already showed, yeah, central harvesting, extraction. Now we did it, analysis. Processing, also we did it. LCMS is kind of a filtering or normalization, alignment, everything. Animal is a pocketing. IR, you need a second derivative. TLC cases, etching effect, or coloring image analysis, something like that processing. Actually, in the conventional study, you don't need it. The processing is kind of a when you are cooking. When you are cooking, yeah, you invite some people. You invite some people. What's the best? First step, you go to the market. You buy best quality of meat, potato, and a carrot or something like that. But this one now you invite people. You cannot serve this carrot, this stem. You have to chop it, right? Because you want to do like some stew, then you have to peel out and chopping. That is the processing of data. But this processing is, of course, now for the stew, you have to cut there's a way of carrot, right? This thing is. But if you want to make a stew very thin, like a very thin, chopped the carrot, it's horrible, right? So that's why this processing is you have to think about the next analytical method. Also, be careful, as I mentioned, once you process data, this processed data cannot store longer. Why? Because once processed, like a carrot or meat, if you cut it, you have to eat within a few days. You cannot store. That's it. And multivariate data analysis actually is not statistics. Multivariate data analysis kind of I'm handling the several variables because I detected thousands of spectrum. I want to use all these variables, yeah, as much as possible. But in our old statistical method, t-test, how many variables you can use it? 1, 2, but ANOVA test, 1 variable, more than 3 groups, Even two-way ANOVA is maximum is two variable. Then MANOVA multi-variable, but is only for the few. Multivariate data analysis. Then why we have to, sometimes some people ask me, some people already students, if you have a data, now Florida orange, Brazilian orange, you measure all the estimates animal skin. So instead of multivariate data analysis, you can do all the details, all the signal, and these two signal is important. These two signal is important. You don't have to do multivariate data analysis, right? Right? Why not?
There are relationships between the variables that you might not consider. The effect of the together actually the response.
This is partly right. Because multivariate data analysis, there is a metabolic variation, but our hypothesis is each variable should be 90 degrees, it's independent one. But in this case, nowadays, I want to do all signal t test because it's a two group t test. I selected which one is as a significant. Then I said, okay, this one is this signal is the characteristic marker for Brazilian origin. But the problem is you already have a prejudice. Before this one, before finding a discovery, you need to know whether Brazilian orange are different from Floridan orange or not. That is the first question, right? But if you go to test, you already did it, they are different. So you just start from this one. But if you have multivariate data analysis, first question is they are separate or not, and then you can find the signal. This is the thing. And also, if he mentioned this one, then multivariate analysis means I want to put orange. It's not one comparator. In the complex structures, they are located one position. That's the difference. So that's why we need it. After that, after multivariate data analysis, probably you found this signal, and this signal can be done ANOVA or t-test. That is possible, but some people does not like it. But at least you can do it. And multivariate data analysis, identification. Now I found this signal is very important. Then identification can be focused on that signal. I don't have to identify the That's what kind of narrow down the signal. So final format of animal is now here, 10 ppm, and each sample looks like this one, and 9.96 ppm. Because I did it every 0.04 ppm, looks like this one. But LCMS cases, now LCMS cases the square, right? LCMS cases. Animal data matrix is 10, 9.96, 9.92, something like this one. Yeah? Then this area, you and this one. But HMS cases or 2D animal cases here. Here, 0 to 10 minutes and molecular weight 0 to 1000. Yeah? Then you have to something like this one. Each one you have to this there, then which means their rate is not 10. 10 minutes molecular weight 300. 10 minutes molecular weight 300. So that's why data, when you convert this 3D data to two-dimensional data, it's a really huge data set. That's the way of the data processing. Then here, when you compare processing, MS data is metabolomics, raw data processing, and filtering, and then feature detection, alignment, normalization. Of course, in between there are many minor processes there. Basically, yes, you have to follow those steps. But animal cases, then some people say, does the animal need alignment? Yes, we need alignment. This one is kind of a marketing. Some people say bidding. This one is alignment. Instead of each signal warping, I don't care. As long as you change within this range. within this way. So that's why animal is pocketing and beating this all together. But this size is very important because if you have a very narrow pocket size, sometimes this over the pocket size, then you have a wrong information. So that's why many people 600 megahertz, 0.2 ppm, or sometimes 0.4 ppm. But some people do it instead of a very broad 0.4 ppm, you are doing like a point here, like this one. Now, even bucket size is like this one, and after this one, after very fine bucket, then you apply the algorithm of alignment. Also is possible. But now look at here. Now this one is a 600 megahertz NMR meter, and this one is pocketing data. Resolution, the problem is resolution completely gone. Now it looks like 80 megahertz NMR because you lost 1 million euro. So this is the why we measured very nice NMR spectroscopy in the cost 1 million euro. But now when you compare to the pocketing, it's a very low resolution because it's just I don't care about within this radio changing. That's what some people want to do with the alignment. But still, as I mentioned, NMR character is 0 to 10 ppm. All the signals there, slight difference can be different compound. If you align strong alignment, probably you will lose very important information. And then your experiments results are based on sampling from the true population. Now, for example, if you do Arabidopsis, you selected three samples and you said it's triplicate. Based on this triplicate, you want to conclude. This doesn't make any sense because ideally, if you want to draw any conclusion like biology or whatever, you have to do all Arabidopsis in the world. You can draw the conclusion. But is it possible? Not possible. So that's the statistics. So you have a very limited number of samples, but your ambition is I want to draw the conclusion very generally. You did the Arabidopsis, but I want to do Arabidopsis. That's it. Then statistic never, so that's why statistics never draw any absolute configuration. Conclusion, it will offer an opinion, and now you found it, Arabidopsis. For example, now you plant, at least you plant. Now you want to report it. That report means it's kind of a suggestion. Can be different. Because you didn't test that plants in the world. And in this world, nothing is certain, but you have to text. One day you will die, you have to text, always simply happen. That's the keep in mind. When you treated one step in the statistical multivariate, there is an error because you did only triplicate among the million of Arabidopsis. So here is very important. You have knowledge about the metabolites. You got it. Second one is you prepare a sample for analysis yesterday, and then you detected all analyzed the method. Now, till yesterday or till this morning, you answered. Now you want to be precise because statistic is basic buzzword is predict. Based on limited number, you have to predict. So now let's think about when you start the science. Always when you want to do science, dreamer. Yeah? You want to dream. I want to be some nice scientist. After that, you met finally your professor, like Fatima. She doesn't care what you think. Always she gave a lot of work. You like answer, you collect the data. And then scientists, you have a theory. That's theory. It's our goal is a theory. Of course, then if you want to believe the church is a truth, but actually it's a religion, it's nothing with the science. Now you are in this area. Science. Because you collect the data with SMS. Once more, this one is prediction. any kind of scientific data treated by statistics, it should predict. Now you have a conclusion. Now I'm based by metabolomics. Each sample contains alkaline, which means it's a predict, which means all other audience or readers they think these plants predictably to contain alkaline. So that which means you need a proof. So role of multivariate data analysis, central harvesting, extraction, analysis, data processing. You chopped it. After that, multivariate data analysis. Now it is in between. Yeah? Because if you have an automatic AI or robot to identify all metabolites, it's okay. You don't need a multivariate data analysis. But in this case, no. Save your time, which signal. Or also even AI, you want to point out which signal is the answer to your question. Yes. So that's why I told you in the beginning that metabolomics, good quality is really dependent on your the question. The best solution is from best question. So if you have more than three factors, the multivariate data. Because ANOVA maximum is two factors. Two factors means two variables. Yeah? Here, there are two kinds of multivariate data analysis. Which kind? They said it's unsupervised method and supervised method. So unsupervised method means now you have people is here. Huh? People here, all the chemical here. I wrote, so baby, my baby or my daughter, daughter, please divide these people. So she divided, she doesn't know nationality, only men and women, right? This is a man and woman. I didn't give any information to her because I just give an order or command. Please divide these people. Then she said, "Oh, she looks like a man, or she looks like a man." It's absurd. She looks like a girl. He looks like a man. Then she told me, I'm not interested in man and woman because I can recognize you look a man, you look woman. But I'm interested in nationality. Then I give her information to her. When you find out her name, please divide them based on nationality. Then I give her another variable. Then she thinks she doesn't care about the gender variance here. Although this gender variation is a maximum variation to separate this group, I ignore only nationality. You look like a Brazilian. You look like a Brazilian. You look like a Korean. You look like a Japanese. You look like a national. That is the unsupervised. Then which one is good for us? Sometimes first step is always unsupervised. Why? Because now you have all the sample, already sample, Now first I learn unsupervised method. Whether Floridan orange or Brazilian orange, Argentinian orange, they separate each other. Lucky case is what I want to know is the maximum variation. That's the lucky case. Unfortunately, you fail in unsupervised method. I cannot see any difference between Floridan orange or Brazilian orange or Argentinian orange. But instead, they are separated based on this the climate. Okay, it's a cold region. This one is warm region or hot region, something like this. In that case, I can apply because my wish separation is not fulfilled. Obtained, cannot be obtained by unsupervised method. I have to use supervised. Then, in that case, this paper is still very nice. Introduction. Here, unsupervised. Please look at this one. PCA. Everything is a PCA. Principal component analysis. But supervised method, which means PCA is a principal component analysis. It's the D method. First is the first step for data interpretation. So then many people say, okay, now I need the PCA. And then I separated them. As in I wish it. Here, Brazilian orange and Florida orange. Very nice. Then, should I go supervised method or not? Usually, you do very well. If you are working for more identification, unless you are working for more identification, separation is PCA is more than enough. But I mean is PCA shows results which you want and it's finished. But because it's not. But some supervised method probably they can increase the power of identification. In that case, you can use it. Here, principal component analysis, I believe this one, principal component analysis, is a data reduction. Some people say strict sense, basic principal component analysis is not statistics. Because PCA cannot predict. For example, now I put the Brazilian orange and Florida orange. Yeah? Very well separate, right? Then if I put apple here, apple, then Florida orange and Brazilian orange is mixed up together. So this is a very relative case. But ANOVA's case is this one is purely is predictable. Now is this group is very different. But strict sense, this protocol analysis is a very relative one. Someone said some debating question is not it's only data reduction. Reduction means 100 of signal to reduce principal component 1 and 2 IQ. And unsupervised degree, like by doctor without information, gender balance, men and women. And nowadays, meta-analysis, right? It's quite open, meta-analysis in mass spectrum, but still is, I prefer Simca. It's it's an expensive one, but it's very user-friendly and graphing is nice.
There are more features, yeah, compared to the double analysis. One styles simple, and they have like different options for see there.
Simca is at least the meta-analysis you don't have to pay. You have to pay. Simca, but for me is also this one is a Simca has a more sophisticated, dedicated OPLS. Actually, OPLS was patented by Simca, so it's very nice. And then graphing, and also you can see how to process data. Because sometimes in the meta-analysis, like CMS, meta-line, you don't know. It's like a black box. How to even though you don't know how to write whether this one is with various scaling or not. But Simca is very clear. This is advantage. But life, there is no free lunch. If you want to take it, you have to pay. The multivariate principal component analysis, you have a lot of data is here. Right? You have a lot of data here. Now you want to compare all these in a based on orange, It's like a juggling. It's too much. Yeah? Because I was too ambitious. You have to reduce like this one. Instead of juggling hundreds of balls, it's impossible, right? I'm not a magician. But if you do one or two, it's easy. But requirement is this one is reduced to the one should contain regional variable. How to do it? Yeah. Yes. So first one is now I explained you normalization. Normalization I explained yesterday against the total intensity, against the interest, against the biggest signal. I explained you this morning. This one, the normalization is to remove sample to sample variation. This is clear. Scaling. Some people confuse scaling and normalization. Scaling is peak to peak variation. This is very different. For example, now here I use to replace this one. Here. Now variable 1, variable 2, variable 3, sample 1, sample 2, sample 3. Variable 1, I did it, I detected 100. And this one is 90. This one is 110. It's variable 1. Variable 2, it's like a flavonoid. This one is sugar, the flavonoid content 10. 9, 11. Variable 3, 1, 0.9, 1.1. Now, if you use this data without scaling, always V1, variable 1 is the biggest defect, right? It's the biggest defect, right? That's not what I want. That's not what I want. In this case, what is the standard deviation of this one? Is 10, right? 10, which means 100 plus minus 10. This one is standard deviation 10, 1. 10 plus minus 1. Right? This one standard deviation 0.1. Right? Then this standard deviation divided by this one. 100 divided by 10. How much is it? 10. This one 9. This one 11. Now 10, 9, 1.1. Sorry, 11. And this one, 1 divided by 0.1, 10, 9, 11. So now, all the signal in the same scale. So it's the same scale. So now, if you don't use this scaling method, you understand this one? So it's a simple method. We call it unique variance scaling method. Unique variance scaling method. Now, here, when it's applied, now is you look at it. Everest Mountain. Yeah? Now, ant. This word ant. But actually, ant is also important. But Everest 2B, if you take the photo from Everest, yeah, this one you can see only Everest. You cannot see this one. That case, you can do this scaling, then ant is getting bigger, Everest is getting smaller, always small scales. That's why I told you in the beginning, normalization is sample to sample variation remove. This one is peak to peak variation remove. You understand? Huh? This one is unique variance method. But what's the problem? There is no perfect method. We call it is a unique scaling method. UV, unique variance scaling method. So first, let's start with the pros, advantage. Advantage, you combine the data. For example, now you want to combine animal data, right? And with the mass data or IR data. You combine the similar set, because you want to have a complete data set. Yeah? But source is different. Source is different. NMR, mass, IR. In that case, you have to use NMR range is this one. Mass range here. IR range here. If you use only this one, then always NMR is bigger effect. In that case, you need the variance scaling it. Right? So that's it. If you want to combine different data, but if you have non-different one, for example, what's the cons? Con is disadvantage. Really, journey. But yeah, no. Think about this one now. I want to unique variance scaling method. It's like a telescope. Yeah? Not normal number. I want to do the telescope. Oh, and I found it. Yeah? I want to only increase the end. Right? But unfortunately, noise also increase. Noise. So that is a problem. Yeah? Existent is okay because it's existent. But I want to increase the journey. But not only journey, there is additional others also noise also increase. So that's why it depends which one. To solve the problem, they divide it not standard deviation, group standard deviation. It's rather mild. Yeah? We call it is a Pareto scaling method. So there are many other methods, but basic one is non-scaling method. I don't want to use a scaling method. Second one is very strong one, need very scaling method. In between, Pareto scaling. Which one is better? I prefer. Or that I mean, spectroscopy data, they said, start with the Pareto scaling method. If it's not working, you can do with the unique very scaling method. Clear? Simple, right? So concept is this one is scaling. So once more, Karen. Carol. 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 So what's the purpose of normalization? Why we have to use normalization? Next is Maria, you have to prepare a bit. Sample to sample variation removed, right? Then scaling. Why we have to do scaling? Maria? Peak to peak variation, like a mountain and keep in mind those things. Do you understand? Next. So after scaling, it looks like this one. This one is not my graph. I adopted from the book, Mathematics Academic book. It's very nice books in here. Now is like an ant. Yeah? And sorry, the Everest. It's ant. For example, this one is glucose level. Glucose is 100 milligram till 90 milligram. And flavulum, 10 milligram till 9 milligram. And plant hormone, 0.1 milligram, 0.00 or something like this one. Then if you do individual scaling, all scaling is the same. So peak to peak variation I do. Yeah. Now is the time to reduce that. Many people already knew about the basic of PCA, right? You know. But Maria, Bruni, have you heard about this way? Johnny? No? Then I started. Here, for example, I want reduce data. For example, now is X, Y, Z. 3 variables. For example, now I want to compare your family and your family height, average height, your father's height, your mother's height, and weight, and food size. Based on this one, I want separate your family, Bruni's family, and Carol's family. So now, based on this one, I pointed here. Now is Bruni's father and Bruni's mother and which one? Carol's mother, father, and something. You can plot it like this way, but then I used all original variables. But this one is only simple example from 3 variables to 1 variable. But actually, if you have hundreds of signal, 100 dimension generate, right? But now it's a simple example for visualization. After that, first step for the data analysis must found the centered one, red one. So if there is a group here is a Burmese family and Carol's family, where the center we can calculate here. Yeah? We can calculate here. This centering is the must have step. After that, this one is moving here. This one, 0 point is moving because it is a centering. Why we have to do centering, I will explain later. After that, still, Bruni has a 3 variable, right? Height, weight, and foot size. Now, I want to reduce the data. How to reduce the data? Here, like I draw the line here to pass the center. It's a maximum variation. We call it a maximum variation. Now, from here, there is a group here. I draw the line, this line. We call it a principal component, one line, like this one. So now we have a group. I draw here. Then the Bruni's father is here. Bruni's father originally have a 3 variable. What's that? Height, weight, foot size, right? Instead of this one, for example, Bruni's father is here. Yeah. For example, Bruni's father is here. Then I draw 90-degree line. Yeah. And instead of Bruni's father as a 3 variables, but now here only from here to here 1 distance. Then instead of 3 variables, Bruni's father has only 1 pixel value, right? Score value. And Bruni's the Carol's father, because father should be he must have three variables. Now instead of this one, 90 degree, then here, from here to distance. Then now, Brumi's father is around minus 10. Carol's father is 20. Oh, they are different. We don't have to use three variables, right? Please look at this one. This one, Bruce's mother, and Carol's mother, right? Then when you inject it, project it on fish one, they are same, right? So that's why in that case you have to draw second physical component line. We call it PC2, 90 degree, because 90 degree. Then Bruce's mother as Carol's mother equal PC2 value, right? So that's why now I want to, this one is only from three variables to one variable. But if you have 100, 1,000 dimensions to reduce to one, it's much nicer, right? That's simple. That's why we have to do this sample, because to draw the line with PC1 line, the vector line, PC1, if you add this one, for example, here, now if you have a line here, mathematically here, now the group is here. There's an empty line here, right? You cannot draw the line because always to draw this line, it should be centered. So that's why centering is must have.
You mean that because if you perform the principal component analysis the way it is, it won't get the maximum possible of the target.
Yeah, that is also. But anyway, important one, centering line, if not important, another line. If not, another line. If not important, another line. But then actually, originally, how many pieces can be calculated is same as original variables, right? If you have a original dimension is 1,000 dimension, you can calculate 1,000 pieces. But now is our goal is data reduction. You don't have to use linkage. Usually, principal component 1 and 2 more than enough. Sometimes principal component 3. So now is another way to do this one. Now A, B, C is animal data. Your mass data, you draw the line. C sample, there are two values. PC1 score, PC2 score, instead of original value. Then question is, now there is all these A, B, C, D, Brownies, errors, family. Instead of original variable, I put the PC1, PC2, PC3, then we can separate it. But the question is, now, Brownies family and Carol's family separate. First question, how they are very different. That's clear. The second question is, what's the second question? Usually, why they are different, right? By weight, or by height, or by foot size. This is very important one. Now, when I check the pieces, here, this one, PC1 is very important to separate this one. Then my question is, original variable x, y, z, height, weight, and foot size, which variable contributes to the PC1 or how much? This is right. Now, Carol's family and the Brownies family separated by PC1 boundary. Then, is that because of height? Is that because of weight? Is that because of foot size? Then you can calculate this alpha value. Now, PC1 generated here, right? PC1 generated here. Original variable is here. If it's a 0 degree, which means this PC 100% influenced by height. Yeah? But if this one is 90 degree, there is no height, it doesn't matter. There are two families have the same height. So that's why you measure is alpha angle. Is alpha angle. If it's a close to 90 degree, then 0 effect. If it's 0 degree, which means 100%. So that's why instead of this, for our convenience, instead of using this alpha angle, we use cosine alpha. So cosine 0, how much is it? 1. Right? Cosine 90, how much is it? 0. So that's why we call it the effect. There are two kinds of data coming out from principal component analysis. First one is score plot. Score plot is here. Now in the Brunys family, father, PC1 score, PC1 score is from here, right? And here PC2 score. So that's why score reduced variable. And second data which you can get from the PCA is loading. Loading means how much influence by original variable to reduce the PC1 loading. Loading is from 1 to -1. Score plot is a reduction. You understand basically?
Back loading again.
No, score plot is, there's no limit, depending on your data unit. Yeah? But alpha angle, alpha cosine alpha is 1 till -1. 1 close to 1 is influenced more. Close to 0, no influence. But close to -1, negatively influence. Influence is always the other two direction, 100% influence and 0 influence, no influence, and negatively influence. Yes. So now, here, principal component analysis. The example, I think it's a very old time I published. I bought the ginseng tablet. From the market, from the drugstore in Netherlands, ABC market, and I measured animal spectrum. I'm interested because they said it's a 16 years old Korean ginseng. But I'm interested whether this one is really same or not. If it's the same Korean ginseng, it should be same, right? I did it here. I measured NMR like this, and then I made a pocket file. D file. I did a fish A, B, C. Completely different one. Even B, to make sure, I bought the two different batch. Yeah? B, first batch, B, second batch. A, first batch, second batch, C, second batch. At least my PC1, B is separated from AC. Which one, right? But now, principal component analysis actually is for the maximum variation. Maximum variation is a very objective one. As it stands, they show, which means sometimes you have to check other binary species. PLS or supervised method, you don't have to do. The first one is always important because you already gave the information. PCA score, we don't know our PC separation, where is it? PC1, PC2, PC3. So that's why you can check it, but most cases, up to PC3 is a 5. But look at this one. Now, A and C looks like similar, right? But I want to test it here. Here. PC1, PC3. Now, A, B, C. It's completely different. What? Which means it's not quality control. Huh? After that, then which means B is separated from A and C by PC1, right? C is separated from A by PC2, PC3. So this one is PC3, Yeah? But this case is, what's the PC2 effect? Benching. Benching, right? So that's why PC2 is related to bench effect. Yeah? Spring, autumn. Yeah? This one, PC1 is a B effect. PC3 is a C effect. Something like that you can divide. Then I measure all the angle, individual angle here. Looks like this one, then this PC1 angle here, higher B, higher C here, like this one. Here, PC1 quartile angle up to 1, yeah, you know, which means this signal is a very high in PC1, which means B has a this positive signal. And if negative signal is high in A. So now I need the mean center, just the centered one, non-scaling method. And this one is Pareto scaling method. This one is unit variance scaling method. More or less, in this case, there's not much effect. But there's difference here. This one is I did it. The perspective I did it with the principal component analysis, loading plot. Loading plot. So when you do Pareto scaling method or non-scaling method, original spectrum is very similar to this loading, so easy to find it. Okay, this one. But now all the minor noise also increased here. So I told you I want the focus, and then all the noise also increased. Process increase. But then it's which scaling method is best? For me, is first to try the Pareto. If it's not working, you can look with the unit variance because it doesn't take so much time. So only one click is enough. Then you can choose which one is good. There's no clear rule which one is better. Here, like this one. No, it's a unit variance scaling method to identify to use loading plot. It's very difficult. Here. So PCA is quite powerful technique. Right? It's very easy and it's very basic, but it's powerful. But what if you have more than 2 data sets? For example, as he mentioned, yeah, now I have data, metabolomic data, bioactivity. Like Florida orange. Actually, you measure the orange, and then without any free information, you draw sample and you separate. But you gave information. Yeah, you gave information, but information is the label. Florida, Brazil. Florida and Brazil. I asked my daughter to separate nationality. Nationality also by value. In this case, here, always multivariate data analysis, what's your interest? Yeah, observation. Now you measure here. So metabolomic is response variable and transcriptomic here. For example, now I measure transcriptomic variable, transcriptomic data, and metabolomic data. Which means sample, I measure animal or mass. I measure transcriptomic data. If this data correlate to each other, probably it's good. Which gene related to which metabolite? Of course, there's a time difference, yeah. But here, so here PCA after PCA. So here correlation between observation and one variable set, correlation between variables in the different data. You have to decide how to do it. And here, correlation between observation, for example, classification, like between sector, like Florida orange or Brazilian orange. This is a classification. Sometimes correlation between observation and variable. So vector analysis and correlation between variable in the different data set. For example, transcriptomic data and metabolomic data. Or you measure, now you have a lot of plant material measured, mass data, and here antimicrobial data, Pseudomonas, E. coli, or the bacillus. activity. Then which signal, yeah, related to which activity. That is nice. So that's why you have to think about what's the goal. Correlation between observation, correlation between observation and variable. Correlation between variable. This is a very important one. And as I mentioned, unsupervised method is a pitch day. But supervised method, a lot. So it depends. Here, but now is many people I said is PCA is the unique one. But actually you can do a lot of analytical tools. But if you are using only PCA, it's not fair. Yeah? It's not after multivariate supervised method, unsupervised method, you have to apply depending on your goal. Now it's choose PCA, you don't have to choose. You have to do that, but then you have to choose several variables here. And limitation of PCA, as I told you, this was a very complex story. But when I give here, only PCA shows maximum variation. Like a ginseng case, what I wish shows in the PCA. This is a very perfect one. But if not, there's a problem, then you can use other data. Like what PLS modeling means, X data. Yeah. Now is without consideration this one, Now I draw the line. This one is like this. But therefore, Y data, draw the line to satisfy both data. This is very important. The PLS, partial list scaling method. Here, now modified PLS method. Now sometimes like yesterday, as I mentioned, now it's to select this one. Now here metabolomic data for this one. Now bioactivity data. For example, 0 to 100%. 0 to 100%. 0 to 100%. In this case, we call it PLS modeling because 1, 2%, 50%, 60%. We combine, then we can correlate. But sometimes, now instead of this continuous variable, now this is metabolomic data. Here is a Korean, yeah, and this one is Brazilian and Japan. Yeah, Japan. Now this sample is Korean. This sample is Japanese. This sample is Brazilian. Korean, Brazilian, Japanese, are they quantitative data? No, because it's qualitative data, like a label. So that's why you have to decide which data it is. Metabolomic data should be quantitative, but additional data set, whether this one is qualitative data or quantitative data. We call it qualitative data is why when you want dummy data, stupid data. Yeah? Yeah? I asked him, he's a Korean artist. His data matrix is, he has 3 variables, Korean, Brazilian, and Japanese. For example, if he's a Korean is 1, Brazilian 0, and Japanese is 0. If it is Brazilian, Korean is 0, Brazilian 1, and Japanese 0. Something like this one. That is a classification data matrix, right? Then, now, when you do just 5 minutes, when you correlate this data, activity data comes out. One data, yeah. So 1%, 0% till 100% by data set. There are several ways you can correlate metabolomic data with the inhibition data itself. Sometimes resolution, sensitivity, the metabolomic data, the biological data is not as much as chemistry data. For example, now your activity is 80%, 80. Yeah? And this one is 79%. 79%. Are they different? Because biological data is very low. So that's why he did it. Instead of this one, I decided 50%. More than 50%, I treat it as active. Less than 50%, I treat it non-active. So that is a data conversion. Then you have a better separation this here. Then the problem is here. You have to decide here metabolomic data is here. Sample 1, sample 2, sample 3. Metabolomic data, blah, 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 is here. Activity data, now is inhibition. Activity data, 10%, 20%, 30%, and 70%. Right? Yeah? You can use this data as a variable. That's the first option. That's the first preference. But the problem is resolution. The resolution is not as much as chemistry data. Then you decided more than 30%, active. Yeah. And less than 30% non-active. Then which means now here is the activity, no zero active, non-active. Active. You can say this one. No, it's not true. If you put A data, activity data 0, 1, it's like this one, you have to think about whether this one is the numeric value or text file. If you put like this way, 0, 1, yeah, then which means this one has a higher one of this one. This one is 2. Yeah? So if this one is a text means now you have two data. 0 and 1, if you treat the different one, you have to think about whether they are related or not. Do you understand what I mean? Yeah. Now, you give a data set, for example, A data, activity 1, activity 2, activity 3, something like this one. If you treat this value as a numeric value, which means 3 has a 3 times higher activity than 1. But if you treat this one as a text, as a non-numeric value, 3 is separated, like a Brazilian. Second is like a Korean. 1 is separated. There is no quantitative variation. So that's why when you convert it to variable, you have to value whether it's a text classification or whether they are related. Now, I gave you activity. Active and non-active. Active and non-active. Then, active and non-active, are they related or not? Yes, it's related because active is higher than non-active one. Then which means 1, 0, you have to treat it as a numeric value. But now it's 1, 0. 1 is Korea, 2 is Japanese, 3 is Brazilian. If you give like this one, you should be very careful. This one is not numeric value, it's the class value, which does not, it's a very independent variable. So when you start into the correlation, you have to analyze what's the factor, what's the character, what's the relationship. This is very important.
For you calculate average of balance and each class balance.
Sorry?
Here you active and inactive.
Yeah.
But before you calculate average of balance and see how balance.
Yeah, that's why in the beginning when he presented I think that my question is when you have a continuous variable, where is the starting point? Is it 30%, 40%? So
Yeah.
This one is you have to have this kind of data conversion. You have to decide. Okay, 30%. I decided this one is active and non-active. You have to give a rational. Then if you don't have anything, I have maybe the normal distribution value. This part more than 95%. I want to use it. It's something like that. You need some clear rational if you want to convert continuous variable to reduced dummy variable. You have to explain. Yeah? Usually, it's activity test we are converting because if you are using 1 to 100%, it's very noisy comes out. Because 79, 60, 79, 80% more or less same, but they treat it different because computer is stupid. That is replaced by. Or, as I mentioned, instead of active, non-active is too extreme. Rather, I give active is 3, Middle active is 2, non-active 1. Then it's a little bit classified this way. 1, 2, 3 is quantitative variable, right? Multi-level quantitative variable. So principal component analysis, multivariate data analysis is great. You can click it, no problem. But how to import your data to the computer is your job. It's very important. It's based on input way, your quality is completely different. Computer never answers to your question if you don't ask. Always, you have to ask question and they give you best answer. So exactly 12 o'clock. Any other questions? Tomorrow, I have 2 hours, right?
Yeah.
1.5 hours. I will continue other one. But today you already did it quite well. All the statistical analysis, really basic. So this is okay. Tomorrow I'll show you some example. And also in the afternoon, it's not course. I'll give a talk what kind of research topic I have applied with this methodology. I'll give you.
There is a question.
Yes.
Yeah.
Lucia, okay? So she said this when you interpret, particularly if someone is not is busy, please speak. I can answer to Lucia. So if you want to interpret data, so then how much maybe I translate, how much influence scaling method, normalization method. So if you do if you don't do normalization, is there any problem? Yes, it's a problem. You have to do normalization. Very careful. But scaling method is to interpret data. Actually, there is no clear rule which one we have to use it. So always I try first with the Pareto, what the unique variance, what non-scaling method, then I try to interpret, then I choose the best one. So nobody complain. Okay, I use the unit variance method. Then nobody asks, why you use the unit variance? Why you didn't use the Pareto method? That's a very bullshit question. Yeah? So you choose the best. This is. Other question?
No.
No.
Okay. Okay, we're finished now, and tomorrow we start again. In the same time, I hope we have state. And tomorrow we have the course in the morning, and in the afternoon, we have a workshop. In the workshop, we have a conference from Choi Game, but it's a title of this research. And we have the other conferences. It's Professor Ian Castro from Guadalajara, Professor I forgot, my God. No, because I go only by many names. Oh my God. Roberto. I, I try to say that no. Because I thought Roberto as a Betão. Oh my God, Betão, no. Roberto Peponini, and then we have Professor Gilberto, and then Professor Moacir. And Aldemir gonna show some results of the the students of it. They will have two parts tomorrow. Okay, see you tomorrow in the afternoon, in the morning, in the afternoon. Today you have activity only in the morning. We finish now. See you tomorrow.